and this is 8.1 in your textbook. We're determining the optimum area and perimeter. First definition, you might not be familiar with the word optimum. It's the most desirable of a number of possible choices. Okay, maybe you are, maybe not. There's a definition there. So our goal is to solve problems involving dimensions of rectangles. So the first they investigate involves three people, Julie, Wyatt, and Nick. And what it tells us is that Julie has a card, and we're talking about a card, of course we're talking about rectangles. She has a card, it has an area of 36 centimeters squared and a perimeter of 24 centimeters. It doesn't tell us the dimensions of that particular card, okay? So it could look like any of these, right? Because as we know, this gives us a area of 36, right? So depending on the orientation of the sides, or the lengths of the sides, you can have different possibilities for that particular card. What I had written originally was going to show you how to figure out how you can find length if you're given width, but then you'd have to actually sub this formula into this formula and you end up with a quadratic. Okay, so it does get a little bit complex, so I'm not going to bother doing that. The way we circumvent that in this lesson is we actually use a bit of trial and error, and you're going to see that in the next example. We actually use a table. So that's Julie's card. It says Wyatt's card wants to have the same perimeter as Julie. She wants to have the same perimeter, but he wants to have the greatest possible area. Okay, so the way we can figure that out is first by drawing different rectangles with the same. Actually, sorry, let's start with Nick. Nick wants to have the same area, but the least possible perimeter. Okay, so the same area as Julie is 36. This is 36 centimeters squared. So what I've done here, rather than having you guys all cut up different pieces of paper, it's going to take some time, I've just drawn out different rectangles with that area. So he wants to maintain that area of 36. So we all know the formula for area is just length times width of a standard rectangle. So each one of these should give us an area of 36. So 1 times 36 is 36. 4 times 9 is 36. 2 times 18 is 36. 3 times 12 is 36. 6 times 6 is 36. Okay? So all of these areas are 36. So we've satisfied that condition that Nick's looking for, the 36 centimeters squared area. Now it says that he wants the least possible perimeter. Well, let's just go ahead and add up the different perimeters. So here we know to find our perimeter, we just add, sum all the sides. So we have 2 plus 18 is 20, plus another 2 is 22, plus 18 is 40. Perimeter is 40. For that one. This one is 36 plus 36 is 72, plus 2 is 74. So perimeter is 74. This one here, we have 9 plus 9 is 18, and 4 plus 4 is 8. So 18 plus 8 is 26. And we've done, well, this one, so 3 plus 12 is 15, plus 15 is 30, so the perimeter is 30. And last one, 6 plus 6 is 12, plus 6, 18 plus 6 is 24. Okay, so we can see here now, if he wants the least possible perimeter, we know it's this one, right? We just know by a simple trial and error. Okay? What do you guys notice about this one? It's got a very special name. Kevin?
It's a square.
Yes, it's a square. Okay, that's not a coincidence. Okay, that's actually what we're discovering here through this investigation, is that if we want the least possible perimeter for a very specific area, then we're going to go with a square. Okay? And it makes sense, right? I don't know if you guys have heard before, but what's the shape that actually produces the maximum amount of area for the least amount of space or material? Anybody know? Josh?
Square.
No.
Oh, like the maximum area?
Yeah, the maximum area for the least amount of material. So if you had a rope and you wanted to create the maximum amount of area with that rope, what would be the shape? Yeah. A circle, right. And you're going to learn that more in depth in grade 10. You're going to actually figure that out using formulas and prove it algebraically. But the closest thing that we have to a circle in terms of a rectangle is a square, right? Okay. You can see here that this perimeter is 74. It's definitely the furthest from a square from all these shapes that I've drawn, right? That's quite evident, right? So the further away you get from the shape of a square, the more perimeter you're going to have, okay, for that particular area. All right, so we know then that Nick's card, he's going to want to have a card that is 6 by 6, a square. Okay, so let's go to now Wyatt's condition. He says he wants to have the same perimeter, so my perimeter is 24, but he says he wants to have the greatest area. So formula for perimeter is equal to 2 times length plus width, obviously, or we just add up all of the sides. So what I did is I drew all these rectangles with the perimeter of 24. Okay, everyone's comfortable with that, right? 9 plus 9 is 18, plus 6 is 24. 6 plus 6 plus 6 plus 6 is 24. 8 plus 8 is 16, plus 8 is 24. So all of these rectangles are variations with a perimeter of 24. Okay, so now we're going to go ahead and solve the area for each one of these. Area is equal to 11, so it's 1 times 11. Area is equal to 20. Okay, in this case, area is equal to 8 times 4 is 32. Area is equal to 27 here, and area is equal to 36. And of course, the units for this are centimeters squared. Perimeter units are just centimeters. Please, please, please remember that, because you're going to lose a mark for that on the EQAOs. Okay, so I can't stress that enough. Area, the units are centimeters squared. Perimeter, centimeters, right? Because it's just a length measurement. All right, so again, what do we notice? If we want to have the greatest possible area, 36, 27, 32, 20, 11, guess what? It happens to be also Kevin?
A square.
Yes, very good. So, it makes sense that they correspond, right? You want to use the least amount of material, and you want to make the maximum amount in the center. They correspond to the same thing. They correspond to a square. Okay, so if you're trying to use the least possible perimeter or the greatest possible area, your rectangle that you're going to use would be a square. Is that clear? Okay, let's move on to a couple examples. So the example says it's a television he's trying to put a screen in. He has an area of 16 meters squared to work with. That's what he's given. And they ask him what dimensions does he want. He wants to obviously have the biggest television to put in that area. So what are the dimensions of his television going to be, or his poster, let's say? And this is all the area that he has to work with. So he wants to maximize his use of that area. So just based on what we learned, what are we going to know then? If he wants to have the least amount of border, so the minimum perimeter. Another way of saying that is the maximum area. What do we know right away? What's going to have to be his dimensions, David? It's going to be square. And to get what's a square with an area of 16, David? Right, exactly. So right away, by just reading this question, based on the definition that you just learned in the theory, you should be able to answer it right away. Well, we know that his dimensions of his square are going to be 4 by 4. Okay? They go through another exercise of finding that out, and they do that by listing different lengths and then different widths, all with the same area of 16. So 1 times 16 is 16, 2 times 8 is 16. Just like I drew the triangle or the rectangles out, they've done that in a table form. Okay, and then they've just calculated the perimeter, again, using that formula. Perimeter equals 2 times length plus width. So they add this up, 16 plus 1 times 2 is 34. Okay, and very nicely in a table, they look at the table and they say, okay, well, we know all of these give us an area of 16. We want the least amount of border. So there it is, and it's 4 by 4. Okay? They even go through the exercise of graphing this. They give you a nice graph, and they pick the lowest point because that's the lowest perimeter, because they're graphing perimeter on the y-axis. Okay? All things not necessarily need to do. You need to be familiar with how to do it if it's asked and what it represents, but not necessarily you wouldn't have to do all that to know the answer right away. Finally, the last little trick in this section. It's important. I'm going to try and cover this quickly. There's a spreadsheet in the book. They do all of the math to figure it out, but I'm going to break it down for you very quickly. We're running out of time here. If you have a rectangle where only 3 sides, you need only 3 sides. So the third side is a wall, an ocean, a lake, a big opening. But you want to maximize the area of a rectangle, but you're only building 3 sides. You guys understand that? You only need to build 3 sides, because the other side you have something else that's already blocking it. You still want to maximize the area. The way you do that is you take your total perimeter. Okay, in this case, I'm just going to finish very quickly here. In this case, they give you 18 meters of wood. Okay, please pay attention, guys. This is important. It's going to be on your EQAOs. Don't pack up. I promise. It's going to be about 1 minute. They give you 18 meters of wood. Okay? And you need to block off 3 sides. The way you find that out, you divide 18 by 2. So divide by 2. That length of 9, that's going to be the side opposite the side you don't need to block off. Okay, so you take your total perimeter, divide by 2, and you got the parallel side to the unbordered area. Okay? What you do with that 9 again to get the other 2 sides, you divide by 2 again. So your other 2 sides are 4.5 and 4.5. Okay, divide by 2, divide by 2. Very quickly in summary. Rectangles with max area, square. Minimum perimeter, square. A rectangle with a border on 3 sides has a maximum area and minimum border length when the side without a border and its opposite side are twice the length of the other 2 sides. So that side twice, these 2 sides. Thank you. Done.